The title of my poster is Confinement and Condensation at Finite Baryon Density in the AdS QCD Hardwall model. This is based on the work done in collaboration with Dr. K.P. Yogendran. The study focuses on the phase diagram of QCD in the baryon chemical potential and temperature plane. A comprehensive understanding of QCD phases and their equations of state is challenging due to the limitations of first principle methods. There are various approaches to studying QCD phases. We study the bottom-up Hardwall model. The holographic Hardwall model relies on a 5-dimensional AdS spacetime truncated at an IR cut of Z0, which breaks conformal symmetry. We start with an Einstein-Maxwell action, where NC and NF are the numbers of colors and flavors, respectively. L is the AdS radius. Theta is a parameter associated with dilatant coupling and compactification of dp branes. Phases and solutions. With this diagonal metric ansatz and gauge field configuration, the model identifies 3 geometries. Thermal AdS, which is a confined phase but has zero density. Charged black hole is a finite density deconfined phase. These two models have been studied extensively in the literature. However, there are no finite density confined phases in any well-established AdS QCD models, except for the work presented by Lee, Park, and Sin. We built on the idea presented there and studied the charged AdS geometry. Charged AdS is a horizon-less geometry at finite density, representing a confined phase that requires us to fix these two parameters Q and G at Z0 by boundary conditions at IR. To fix these boundary conditions, we demand that the equation of state obtained from the Hardwall model matches with QCD phenomenology results in their region of validity. For instance, Nambu-Jono-Lasignol's model at finite temperature and chemical potential is matched where we expect quarks as degrees of freedom. At low densities, baryons are described by the isospin symmetric in medium chiral perturbation theory, which shows van der Waals type behavior. Comparing different geometric solutions, we obtained this phase diagram. The phase diagram includes regions for quarkionic matter, deconfined quarks, baryon liquid, and baryon gas. The red curve separates the charged AdS phase with different boundary conditions from the charged black hole phase. The phase diagram is in agreement with the results from the PNJL model presented by Coster and Pereira. Incorporating condensates. The model introduces a complex scalar field psi to explore symmetry breaking. Here delta is the scaling dimension, and psi is charged under U1b. The spontaneous symmetry breaking requires non-normalizable mode to 0. We present numerical solutions as a function of radial coordinate z. Different color represents different boundary values of psi at IR cutoff. Here the maximum pressure solutions are identified to fix the boundary condition for the scalar field in the charged AdS geometry. It is shown by the black dashed curve. Operators corresponding to NJL and van der Waals models differ in charge Q and scaling dimension delta. There exists a range of scaling dimensions allowed by thermodynamics. The phase diagram highlights how different condensates emerge in various regions of the mu-BT plane. We can see that condensate always exists at low temperatures and high densities. Conclusion and future directions. The study demonstrates that the 5D holographic Hardwall model effectively captures low-density confined phases in QCD and baryonic condensates with varied charges and scaling dimensions. These are some future research avenues.